What's up, everybody? Dan Foot here with another video trying to explain the solid principles of object-oriented programming, with a few examples in there for a few of the principles that I thought would be best to explain with a little bit of code. So let's get right into it. Now, what are the solid principles first? Well, it's an acronym that was coined by Robert C. Martin, aka Uncle Bob here. Now, Uncle Bob has written a number of books. I highly recommend reading them. I'm making my way through them right now, and they're very well written, and they will change the way that you look at software. Now, the solid principles were designed to make the software more understandable, flexible, and thus maintainable. So this means this is like the opposite of what you're probably looking for right now, because in school, what do we usually do? Take the shortest route possible, write as few lines as possible, just get it to work, right? Well, when you start to work on an actual big project, something like you would do in your software engineering classes, you're gonna want to think about making your code more understandable and maintainable because you will be doing those things. Now, I know all your previous assignments all been throwaway work, but now, from now on, you need to start thinking about maintainable, and that's what the solid principles will give us. Now, SOLID is an acronym. So, single responsibility principle, the open close principle, Liskov substitution principle, interface segregation principle, and lastly, the dependency inversion principle. And we'll go through them all one by one. All right, let's get started. All right, the single responsibility principle. A module or class should only have a single responsibility provided by the software. So basically, the software that you're writing should only require any single module or class to do one thing and one thing only. It should do that one thing extremely well and nothing else. So no more just shoving more things inside of a function just to make it easier so you don't have to write as many functions. No, that's bad because then you go to update it, eight other things could break. That's bad. Now, a quote from Uncle Bob himself: gather together the things that change for the same reasons, separate the things that change for different reasons. So, again, it's all about organization. If you touch something that's unrelated to a bug that you're trying to fix, you're more than likely going to create a bug in another area, right? And because of this, if you organize things that change for the same reasons, when you're fixing a bug, you'll easily be able to chase it down, fix it, and if you do happen to create another bug, it'll be something in the same realm as the original bug, and thus you'll be able to spot it. You won't create a bug that you'll discover 3 months down the road. All right, so for the single responsibility principle, I came up with the idea of we have a contact card here. Now, this contact card has a name, an address, and a phone number, right? But let's pretend that one of the business decisions was that this phone number has to be validated. We have to validate it using this regular expression. Now, this regular expression, all it does really is says we need 3 digits, a hyphen, 3 digits, a hyphen, and then 4 digits. If it doesn't follow that format, then it throws an exception. It's just as bad phone number. Okay, now, this is fine because there's not much going on here. We could do this, but if we follow the single responsibility principle, we can see our new code here. We actually take the contact card and we replace, instead of passing in just a string for the phone number, we pass in a new phone object. Now, the phone object itself actually has the pattern and it does all the same things. So when we instantiate a phone number, we pass in the phone number and we match it. Does this match? And if not, throw an exception. And then we set the phone number and we have a little getter so that we can get that phone number back out. And what this does is it gives us the ability to move the logic to where it actually makes sense. What if in the future we wanted to only accept phone numbers from certain area codes? Cool, I'll do that right here in the phone object. That would make sense to throw it right in here, right Right when we're creating the phone number, we'll just check, are the first three digits what that's on the approved list. The other thing that you would have to consider is our contact card. Well, what if we wanted to add more things to this? What if we wanted to add a home address versus a work address versus a mailing address? And we wanted to have certain restrictions on that. And what if they decided, oh, business comes back and says, you know what, I actually want you to validate and make sure that you have a valid address. Here's how we can do it. Okay, well, where would we put that? Would we want to clutter up this? I mean, because now we're checking if the phone number is good, if it's in a certain format, if the area code is one of the accepted area codes, and now if the address is accurate. Man, this contact card is going to get massive. But if we move it to the place where it makes sense, the phone will change for all the same reasons. Anything that changes in here will change for the same reason because the way that we're processing phones, phone numbers, or validating phones and phone numbers will have changed. So it makes sense for us to pull it out. Okay, now the open and closed principle. The classes should be open for extension but closed for modification. What does that mean? Well, basically, it's just that you should be able to add new features without modifying existing code. Now, this is a big one where the example will really help you to understand it. But basically, what I want to get across here is that you should think about extending existing functionality without modifying the existing code. This is good in principle when it comes to maintaining code because if you organize it in this way, you won't have to touch existing code. If you don't touch existing code, and assuming that it works to begin with, right, you won't break it. So adding new features or extending the code should not break existing features. Now, in practice, that does happen, but if you follow the open closed principle, it shouldn't happen nearly as much. All right, so let's get to that example. All right, so for this example, we're going back to the old reliable shapes examples, right? So let's pretend that we have an array of shapes that we want to calculate the total area of all the shapes added together. Well, to do that, we would have a function similar to this. We would have shapes coming in, just saying that they're generic objects and it's an array of them, right? Now we would have a total area, and for each of the shape in shapes, we would say, well, if this is a rectangle, then we calculate the area by doing this. So we would say, well, this is a rectangle, so let's cast it as a rectangle, store that, get the height times the length, and then add that to the area. Okay, well, if it's a square, well, how do we do that? Well, we just cast it as a square. We would just get the length and then multiply it by the length again and then add that to the total area. And if it's none of those things, well, then we have an issue, right? This is not a shape. And then we would return that total area. Well, so our classes would look something like this. We'd have a rectangle here, we'd have a length and a height, get length, get height, and then we'd have a square which has just a length, right? And just a get length function. Okay, that works perfectly fine, right? But what if we come back with, well, we want to add triangles, we want to add trapezoids, we want to add all kinds of stuff. Are we just going to keep adding to this list of if else this if else block and just keep adding shapes? What if somebody throws something in there because they think that we have the code to calculate the area of the trapezoid, but we didn't add it? It's going to throw a runtime exception now. Well, that's not good either. Is there a better way to do this? Yes, using the open closed principle, we would remake it like this. So, starting from top to bottom, we would say, so our total area function is going to change. It's going to accept an array of shapes instead. So here's our array. The total area is the same, but for each shape in shapes, we're just gonna add to the total area shape.getArea. That easy, and then return total area. So you can already see that this code is much simpler. But where did that code go? Well, it went into the classes themselves. So we defined an interface, a shape. Now, what does it mean to be a shape? Well, it means that you have a way of calculating the area, right? At least for this example. It means a lot of other things, but for this example, it just means that you should know how to calculate your area. By the way, if you don't know exactly what an interface is, we will be going over that very shortly. So just try to follow along and just think of it as a basic contract that says that you need to implement this. You need to implement a get area function. And then here we say that a rectangle implements the shape contract or the shape interface. And what that means is we need to actually make this get area function that returns a float. So we did that, and a rectangle is length times height, which we do right here. And a square, we did the exact same thing. This implements shape, and it has a get area function right here, and that returns length times length. And there we go. So now any shape that we pass in here, well, it has to be a shape. It has to implement the shape interface, otherwise it's not a shape. Thus, nothing that contains an array of anything other than objects that implement the shape interface, you won't be able to call this function. If you can't call this function, we're not going to throw any errors. And if we don't throw any errors, that's great. And the other thing is, if I wanted to add a triangle, all I would do is I would just come down here and I would do public class triangle implements, and then I would do shape. Now, when I do this, it's not going to let me compile until I actually add the get area function. And that's going to prevent any errors from happening. And if I go and add 18 more shapes, I don't have to touch this code. This code works. This code works. It should not be touched. If we make a mistake and we forget to update this area to account for the new object, that's not going to happen anymore. That is the open close principle, and it's going to save you a lot of trouble. All right, so the Liskov substitution principle says that if A is derived from B, then A should be able to be used anywhere B is used. So what this means is direct inheritance isn't always the answer. Sometimes an interface should be used to bridge two objects together to make them related. Now, I know that this is where the complexity of the principle starts to really escalate. So if you don't understand that right away, let's go into the example, and you might need to mull this over for a little bit. So if you're confused, trust me, you're not alone. All right, let's get to the example. All right, so when looking at the Liskov substitution principle, we're going to take some more a more wide view rather than specific code examples. So what I have here is a public class bird. Now a bird can fly, right? So we implement, here's how a bird flies. Just do some flying, right? Implementation doesn't matter. Now we also have a duck. Now a duck is a bird, so it extends bird. So now the duck can fly. Now, what are some other birds though? Let's look at ostrich. Ostrich extends bird. Wait. Now the ostrich can fly because it extends from bird. So I feel like we're missing a piece here, right? Ostriches don't fly, but it is a bird. So something's wrong with the way we have this set up. So let's take a look at the solution. Now we declare bird class, right? Then we say, well, now we have a flying bird class which extends bird, which now has the fly method on it, does some flying. And now the duck extends from flying bird, whereas ostrich extends from just bird. We can treat duck and ostrich both as birds, but we can only treat duck as a flying bird because duck is the only one that can actually fly. So this makes sense again, thanks to the Liskov substitution principle. So basically, our issue was anywhere that we would have a flying bird, we should be able to substitute a duck in there and everything should work. And everywhere where we had a bird, we should be able to substitute an ostrich and it should work. But if we flip back to our old example, it doesn't make sense because for our ostrich here, we would have to remove the ability to fly. We would have to just like break it somehow, like remove the method, which we couldn't remove it, but we'd just make it a stub rather than it actually doing anything. And then, so we would be absolutely violating the Liskov substitution principle because we would not actually be able to replace all birds with ostriches. I hope that that cleared it up. All right. Now we're on to the interface segregation principle. Now, the interface segregation principle says that no client should be forced to implement methods they will not use. This kind of makes sense when you read it, but uh, it's not always the most obvious thing. So, if we have an interface, a monolithic interface, we should slice it down into more specific interfaces and just implement multiple on objects that require multiple so that we can create objects where it only makes sense for us to implement one of them on some of our more specific objects. And we'll see this. We're going to go right back into our shapes example, and we will look at an example between 2D and 3D shapes, and how if we slice the interface down, we can make it more specific and thus have more control over our code. All right, let's get into that example now. All right, so looking at the interface segregation principle, we're swapping back to shapes again. Now, a 2D shape, you can get the area. A 3D shape, you can get the surface area, right? But only for a 3D shape can you get a volume. A 2D shape doesn't have a volume. It doesn't make any sense. You can't fill anything in it. But for our interface here, we've decided, well, we have shapes, some of which are 3D, and we need to get the volume. So we just slap that onto the interface, right? No, that's definitely not the right way to do this, and it breaks the interface segregation principle because now we would have 2D shapes that would have to implement a get volume, which would have to do something. It would have to throw an exception maybe, or just return zero. I don't know. I don't know how we would do that. So anyways, let's flip over to the solution, which is basically just let's split it up into two, right? We would have a shape, which we could call shape 2D if we wanted to, but I wanted to keep this consistent with the last one, so we would have the exact same, you would have the same getting the area, and now your 3D shapes would implement this interface as well, the shape 3D interface, so that they would have to put a volume. Then you could calculate the total volume of a collection of 3D shapes the exact same way that we did with the area of 2D shapes in a previous example. And you've just segregated your interfaces to make them more specific. And there's nothing wrong. You can absolutely implement a dozen interfaces on a single class. That might be getting up there a little bit too much, but it's possible. And the moral of the story is that you should absolutely separate these things whenever possible because it will make future enhancements easier to implement. All right, so lastly, the dependency inversion principle. Now, what it says is that high level modules should not depend on low level modules. Both should depend on abstractions. Abstractions should not depend on details. Details should depend on the abstractions. So, what does this mean? Well, the last point here summarizes what this means. So, when depending on abstractions, you can change implementation details all without modifying the surrounding code. Now, for this one, I don't have a specific coding example, but I do have this image here, which I think really summarizes it, which is that your lower level classes should depend on and expect interfaces rather than pointing directly to the high level class, and that high level class should implement that interface the contractual agreement so that you can inject the high level class into the low level class, and there's absolutely nothing tying them together specifically. What does this allow you to do? Well, if you wanted to change your high level class, like let's pretend that high level class is how you store data in the database, and you wanted to change from a SQL server over to MongoDB. Well, you would just change your high level class, implement the exact same interface, and you should just be able to swap those out, and everything should still work the same because as long as you're still fulfilling the contract in the interface exactly the same way. So, that is the dependency inversion principle. And next up, we have a quick summary of all the solid principles. All right, so to do a quick summary, we just went through all the principles of SOLID, and first we have the single responsibility principle. The single responsibility principle, of course, says that any module, class, or function should have one single job. So if you find that you have a class that has multiple jobs in it, you should split it up into at least two, if not more classes, each with one responsibility. Next, we have the open closed principle, which is open for extension, closed for modification. So you should set up your code in such a way that you can extend it but not need to modify the code. Third, we have the Liskov substitution principle. Liskov substitution principle, of course, is the if it looks like a duck, quacks like a duck, but if it takes batteries, you're probably using the wrong abstraction principle. Then fourth, we have the interface segregation principle, which says that you should not use monolithic interfaces and you should definitely not implement methods on classes that will not be used just because the interface says that you need it. Instead, you should think about taking that interface and breaking it into multiple. Then lastly, we had the dependency inversion principle, which basically said that low level code should reach up to higher level code, and high level code or higher level code should never reach back down. It should be a one-way street. All right, and that's going to sum up the solid principles. I hope you learned something today and have a great day.